Okay, folks, today we're going to go ahead and continue on with our kinematics that we've been talking about, but the only difference today is that we're going to talk vertical motion, which means things moving up and down, in particular things being dropped through the air or throwing something up into the air. And we're going to look at a big concept called free fall, which ties in hand with vertical motion. So let's look at what's going to stay the same for us. And if you look, obviously, your kinematic quantities do not change from last week. The only thing that is going to change is the cosmetic look of your equations. And what I mean by that is that instead of IDing your displacement with the symbol x, like we've been doing so far, you're going to substitute the symbol y in, y being for vertical motion, x being for horizontal motion. Now, is it a necessity to do? No. As long as you keep your numbers straight, you should be good. But when we move into 2D motion, then it will be a necessity to keep your x horizontal values straight versus your y vertical values straight. So let's look at some new things here that we have to keep track of. First off, things that are falling will always have a negative velocity, which should make sense to you because if we're talking vertical motion, up is our positive direction, down is our negative direction. Dropped things will have an initial velocity of 0. V of I equals 0 meters per second because they're going to start from rest. This is really important here. Final velocities, when they hit the ground, you cannot say your V of F is 0 meters per second. Think about it. If you were to drop your cell phone onto the ground, when that cell phone hits the ground, it just doesn't stop dead in its tracks. It does a little wiggle or shimmy or shake or maybe bounces up a slight bit. Anything that you drop, when it hits the ground or the surface, is going to have some slight movement to it still. So you cannot say V of F is 0 when it hits the ground. And then lastly, if a problem is classified as free fall, your acceleration value will always be a constant value, meaning the same. So let's go ahead and take a look at what free fall means. So free fall is a special case of vertical kinematics where the only thing accelerating your object is the force of gravity. To put it simply, anytime you drop something and it's falling through air, it's technically in free fall because the only force that should be acting on it is gravity, which is pulling it down. It doesn't matter what got the object moving. All we care about is as it's falling through air, is the only thing acting on it gravity. Therefore, we say it's in free fall because gravity is the only thing causing it to accelerate. Now, in order to have free fall, true free fall, we often have to ignore air resistance. So often in physics problems, you're going to see at the end of the problem, ignore air resistance. And that is because when you have air resistance, you have other forces coming in and playing a role. And then if that is the case, you're technically not in true free fall. So we always ignore air resistance so that we are in true free fall with gravity the only force causing that object to accelerate. So, the acceleration due to gravity, as I said before, when something is in free fall, that acceleration due to gravity will always be a constant value. It has a value of negative 9.8 meters per second squared, or oftentimes folks will use negative 10 meters per second squared. Why? Because negative 10 is the rounded version and it's easier to use. I will use negative 10 always, just by personal choice, but you can use either or. It doesn't matter. They're both right. Just keep in mind if you use negative 9.8, your answers will be slightly different than mine because of myself using the negative 10. Now the thing is, you will never see this stated in a problem. They're not going to come out and tell you you're in free fall. You have to recognize the object's in free fall and then automatically in turn recognize that the acceleration is the negative 10 meters per second squared. So we're going to go ahead and work through our example problems now. And I do have a video clip from the Pirates of the Caribbean. And we're going to use our kinematic equations to find how far Elizabeth Swann fell and how fast she was going when she hit the water. The only thing is, you're not going to watch the video clip. We're going to go ahead and just work right through the problem here. So here we go. If you ever saw the movie, Elizabeth Swann was standing on top of a cliff and she jumps off into the water. So when she's on top of the cliff, her V of I is 0 meters per second. She's at rest. She is in free fall when she jumps off, so acceleration is the negative 10 meters per second squared. And if you actually timed it with a stopwatch of some sort, it takes her 4.63 seconds from the top of the cliff to her falling through air to when she hits the water. So we want to find what's called her impact velocity. Impact meaning upon impact of the water, how fast is she going? And which would be her V of F, her final velocity. So if you look, we have no position values here. So therefore, that means we are using equation number 1. V of F equals V of I plus A times T. And remember, your initial velocity is 0, so we can get rid of it. And so therefore, this is all we have left. And then therefore, we can go ahead and we can plug and chug our numbers. So A is negative 10, and time is the 4.63. And therefore, you get a V of F of negative 46.3 meters per second. And remember, it should be a negative velocity because she is falling down, down being our negative direction. All right, the next thing we want to figure out is how far did she fall? Let's write some knowns down. She's still in free fall, so therefore the acceleration is negative 10 meters per second squared. She's still starting from rest, so her initial velocity is 0 meters per second. We still have our time value of 4.63 seconds. And the position values here. So if you think about it, when we're talking vertical motion, when an object hits the ground is considered our surface. And in this case, the water is our surface. And we consider that the 0 mark. So her final position, her Y of F, is 0 meters because she does hit the water. So what we're actually trying to solve for is her initial position, meaning how high up is that cliff she jumps off of. So if we know how high up the cliff is, isn't that how far she's going to fall down? So Y of I is our unknown. So if you think about it here, we can't use the first equation, okay, because we're trying to find Y of I. We technically could use the third equation. We have everything we need, and we could use the second equation as well. So I'm going to go with the second equation. Y of F is equal to Y of I plus V of I times T plus 1/2 AT squared. And I'm going to get rid of my 0 stuff. So I have Y final is gone, and then my initial velocity, this chunk, because 0 times anything is 0, is gone. And so what you have left here is 0 equals Y of I plus 1/2 AT squared. So what I'm going to go do here is I'm going to leave Y of I alone. He's already positive over here, so why mess with him? I'm going to move this whole chunk to the other side of the equal. So I have a plus 1/2 AT squared, so I'm going to subtract it over to the other side. So minus 1/2 AT squared is equal to Y of I, and we are ready to start plugging. So minus 1/2, A is negative 10, T is 4.63, and that is squared, equal to Y of I. So if you work that out, you get the negatives that turn to a positive, and we end up getting a distance of 107.18 meters. So that is how high up the cliff was in turn, which means that's how far she must have fell. Okay. Now, our last 2 slides are actually connected here, so we're going to go ahead and start with this problem about the Olympic diver who's stepping off a 10-meter tall platform. And I want to know the impact velocity when they hit the water, and I want to know how long it takes that person to hit the water. So we're going to go ahead and write down some knowns. So with that being said, we know that the platform is 10 meters high, so that's where the diver is starting. So Y initial is equal to 10 meters. We know the diver is going to hit the water once again, the water being our surface, or aka the ground level, so we're going to call that Y of F 0. Obviously, the diver is going to be in free fall, falling through air, so A is negative 10 meters per second squared. And then the diver is going to start from rest, right, at the top, so the V of I is 0 meters per second. And we want the impact velocity, meaning how fast is the diver going upon impact of that surface, aka the water. So we want our V of F. Now we have no time values here, so automatically it's got to be equation 3. So for equation 3, VF squared is equal to VI squared plus 2 of A YF minus YI. And let's go ahead and get rid of our 0 stuff. So we know the initial velocity is 0, and we also know that the Y final is 0. And so I'm going to rewrite this to clean it up. You have this left. And now we can go ahead and we can plug away. So 2 times our acceleration times that minus y of I, and y of I was 10. And now solve that out, and you get 200. And then obviously to get that v of f by itself, we need to square root that 200. So v of f is going to equal 14.14 meters per second. Now here's the thing. Remember, when you're using equation number 3 and you're solving for v of f, which we are in this case, and you know your object's moving the opposite way, you need to put the negative back in your answer. And our object is moving the opposite way. In other words, it's moving down, and down is our negative direction. So our answer is actually negative 14.14 meters per second. And now if you look at part B, we want to know how long does it take the diver to hit the water. So we are actually solving for time. So in part B, we want time, and right away I see that I have a v of I. I now have a v of f. I have an a, so that fits my first equation perfectly. So v of f is equal to v of I plus a times t. And we're going to go ahead and solve for t. I can get rid of this v of I because it's still 0. So all I need to do to get t by itself is divide a over to the other side. So v of f is a negative 14.14. The a is negative 10. Thank goodness those negatives cancel out because you can't have a negative time. And you get a time of 1.4 seconds. All right, our last problem here. It says, after hitting the water, this diver is brought to a rest being the key word, 2.1 meters below the surface of the water. I want to know how much acceleration did they experience. Let me draw you a quick little sketch over here of what's happening. Here's our water, and in the problem above that we just did, we were concerned with this part of the trip, the diver jumping off the board and falling down to the water. Now in this problem, it says after hitting the water, they're going 2.1 meters below the surface. So 2.1 meters below the surface of the water. So really what we're concerned with is the start of the trip being right here where the person hits the water to the end of the trip where the person's brought to a rest 2.1 meters below. So we only want this part of the trip as the focus in this problem. So let's write down our notes. We don't know acceleration, and our v of f, our final velocity, well remember they're brought to a rest at this 2.1 meter mark below the water, so v of f is 0 meters per second. But our v of I, be careful here. Remember, our v of I in this part of the trip is the moment they hit the water, which is a continuation from the problem up here. So we figured out that the v of f in this problem when the person hit the water is negative 14.14. Well, now that v of f becomes our v of I in this portion of the problem. So v of I is at negative 14.14 meters per second. And let's get our position values. Our y of f, they say the person goes 2.1 meters below, so 2.1 meters, but it's a vector, right? And the person is going down, 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 so you need a negative on there. And then your y initial, well, y initial, this is the starting point of our trip right here. Y initial we would just call 0 meters. Okay, so no time values, so once again, oops, let me move this up here. So no time values, so once again, we are going to have to use our third kinematic equation. Scoot this over. So we're going to have VF squared is equal to VI squared plus 2A y of F minus y of I. And then get rid of your zeros. So this time our final velocity is 0 and our y of I is 0. So that minus y of I is gone. So I'm going to clean this up. We have nothing left on this side of the equal. Vi squared plus 2a y of f is what's left. So here we go. We want a. So I need to move this vi squared over to the other side by subtracting them over. And then you have this left. And then we need to get a by itself. Everything's being multiplied right here. So just divide 2yf over to the other side. And now you can go ahead and plug and chug. So we have a negative. That vi was also negative. So 14.14 squared divided by 2 times y of f, which was negative. And if you work that out, be careful here. This negative squared does become a positive, but you still have that negative on the outside of the parentheses. So technically you still end up with a negative divided by a negative, and your acceleration does come out then to be positive, 47.6 meters per second squared. Now, that should be positive. Think back to chapter 1. Person hits the water and is still moving down, so therefore the velocity is down, but the person's slowing. It comes to a rest about 2.1 meters below the surface of the water. So remember, anything that's slowing down and coming to a stop in life has to have the velocity and acceleration vectors pointing opposite ways. So if velocity is in the direction of down and the person's slowing, then acceleration has to be in the direction up. Therefore, yes, we have the positive value for acceleration. If the acceleration wasn't in the positive direction, this diver would keep going down, 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 down forever in the deep ocean waters. So we are good with what we got. Okay, that is a wrap.